So today we are going to start with one of the chemical properties of phenol, second chemical properties of phenol. We've already discussed yesterday one of the property of phenol, if you remember. We discussed the acidic nature of. So today what we are going to discuss is the electrophilic substitution reaction in the case of phenol. We are discussing the second reaction of phenol, that is electrophilic substitution reaction. Remember electrophilic substitution reaction? We have to do four reactions, namely halogenation, nitration, sulfonation, and Friedel-Crafts reaction. First of all, we will find out phenol, that is benzene with OH. Now everyone knows this. Directly on the benzene ring. Reacts with electrophile, something with a positive charge. Which are the positions which will be attacked by electrophile? There are three possibilities. Electrophile can attack at ortho position, meta position, and the para position. So we have to find out at which position the electrophile is going to attack on phenol. There are three possibilities. Either the electrophile can replace hydrogen from this position, it can replace hydrogen from this position, or from this position. We are just going to prove it that over here the attack will not be taking place. Over here only the hydrogen will be replaced by electrophile, or in the para position the hydrogen may be replaced by electrophile. So when phenol undergoes reaction with electrophilic substitution reaction with electrophile, we get the mixture of two products. The hydrogen from the second position may be replaced by H plus may be replaced by electrophile. We can have electrophile in the ortho position, we can get an ortho product. Or the electrophile may attack at the fourth position, that is at the para position. So phenol undergoes electrophilic substitution reaction at ortho position and the para position. And the reaction is very fast. Meaning by phenol is actually activated towards electrophilic substitution reaction. We are going to prove this right now. And as I told you, we will be discussing four reactions, electrophilic substitution reaction. One by one, we will be discussing halogenation. We will be discussing nitration. We will be discussing sulfonation, in which SO3H groups attach. And we will be discussing a reaction called Friedel-Crafts reaction. So just to revise, number one, phenol undergoes electrophilic substitution reaction at the ortho and para position. You will get a mixture of ortho product and the para product. And the reaction is going to be very fast, because we are just going to prove, just like in our case of aromatic ether, phenol is activated towards electrophilic substitution reaction. So let us prove why phenol undergoes electrophilic substitution reaction at ortho and para position, and why it is going to react at a very fast speed. For that we need to draw again the resonating structure of phenol. So let's draw the resonating structure of phenol. So if you draw the resonating structure of phenol, as we have done in the last class, there are five structures. In phenol, the OH group shows plus R effect. It gives electron to the benzene ring due to resonance, as it has a lone pair of electron. Lone pair becomes a bond pair, and bond pair becomes a lone pair. So this is the second resonating structure that we have. This will become a double bond. Oxygen will get a positive charge, formal positive charge, formal negative charge. Let's move further. Lone pair becomes a bond pair becomes a lone pair. So this is the third structure. And the fourth structure. And the last structure. So if you draw the average average structure of the resonance hybrid, it will look like this. Average of all the 5 structures that we have. All partial double bond with a small positive charge over here, small negative charge at the ortho position, para position, ortho position, ortho and the para position. So you can see from the resonance hybrid, due to resonance, ortho positions and the para position gets a negative center, act as a negative center. So common sense, something positive will attack on the ring either at the ortho position or at the para position. So phenol undergoes electrophilic substitution reaction at ortho position and para position. Because due to resonance, ortho and para position act as a negative center. So the first thing we can write down over here is in phenol. As I told you, OH group shows plus R effect. OH group shows the plus R effect, and thereby, due to resonance, the ortho and the para position act as a negative center, So electrophile attacks on phenol at ortho position and at the para position. Ortho and the para position. Now the second point I like to discuss with you, apart from that phenol undergoes electrophilic substitution reaction at ortho and para position, or the OH group is an ortho para directing group. You can see over here, the OH group is giving electron to the benzene ring. If OH group gives electron to the benzene ring due to plus R effect, what is going to happen on the benzene ring? Electrons will become more, negative charge will become more. So naturally the attraction of benzene towards positive will increase, or its attraction towards electrophile will increase. So OH group tells benzene, go and react with the electrophile. And whenever the group tells ring, go and react with the electrophile, the group is said to be activating ring towards electrophilic reaction. So the OH group, since it shows plus R effect, increases electron density on benzene ring. It tells benzene ring, activates benzene ring to react with the electrophile. So the rate of this reaction is going to be very, very fast. So this is the first point, that in phenol OH group shows plus R effect. So thereby due to resonance, ortho para position act as a negative center. So electrophile attacks on phenol at ortho and para position. What is the second point? We can just modify this one, that in phenol OH group shows plus R effect, and what happens? The OH group increases, this is a sign for increase, increases electron density. It increases electron density on benzene ring. Electron density on the benzene ring. So it activates or tells benzene ring, activates benzene ring in phenol, the benzene ring of the phenol, benzene ring in phenol towards electrophilic substitution reaction. So we have discussed 2 points, just like we have done in the case of aromatic ether. In phenol, electrophilic reactions happen at ortho and para position. And secondly, the benzene ring in phenol is activated towards electrophilic substitution reaction. Reason being, OH group shows plus R effect. Whenever the group attached to the benzene ring shows plus R effect, the ring is activated towards the electrophilic substitution reaction, or the rate of the reaction is going to be really very, very fast. And it is always an ortho and para directing group if the group gives electron or shows plus R effect. There is one exception which we are going to do in a halide, but that we will discuss later on. Let's now start with the examples of electrophilic substitution reaction in the case of phenol. As I have told you, we will be discussing 4 reactions, always electrophilic substitution reaction, halogenation, nitration, sulfonation, and Friedel-Crafts reaction. So let's start with halogenation. I'll take the example of bromination. Let's take the example of halogen, bromine, and react with the phenol. So the first one we are discussing is halogenation. We are going to react phenol with a halogen. Example like bromine. So what you do, you take phenol, having benzene ring highly activated, react with bromine. Suppose we are doing the reaction in a polar solvent, water. We are doing the reaction in the polar solvent, that is water. You will find all the ortho positions in the para position. 2 ortho and the 1 para position. All the hydrogens which are present over here, over here, over here, they will be simultaneously replaced by Br. So basically what is going to happen, 3 hydrogens simultaneously will be replaced by Br. We get a tri-substituted product. The H from here will be replaced by Br. H from here is replaced by Br. H from here is replaced by Br. We get a formation of tri-substituted product. Tri-substitution takes place. All the ortho and para positions are simultaneously the hydrogen H plus replaced by Br plus. What will be the IUPAC name? 1, 2, 3, 4, 5, 6, 2, 4, 6. So it will be called as 2, 4, 6 tri-bromophenol. And in fact 2, 4, 6 tri-bromophenol is a white PPT. So it can also be taken as a test for phenol. Phenol, if you put bromine water or any unknown compound when you put bromine water, if you get a white PPT, the compound may be phenol. Phenol gives a white PPT with bromine water. Now let's find out if we use polar solvent, why do we get a tri-substitute product, or why all the 3 hydrogens get simultaneously replaced by Br. What is the reason for this? What happens is, if you are working in a polar solvent, in polar solvent, phenol is not present in this form. Phenol, in the presence of a polar solvent, the OH bond of the polar solvent will ionize. So in the case of polar solvent, phenol will be present as a phenoxide ion. It won't be present in the unionized form, doesn't exist as phenol, but it is present in the ionized form, that is phenoxide ion. It exists as phenoxide ion. It occurs as a phenoxide ion in the presence of water, which helps in the ionization of the OH group. Water helps in the ionization of the polar bond, and this bond is a polar bond. So in water, phenol exists as a phenoxide ion. So what is so special about phenoxide ion? You can see in phenoxide ion, we have oxygen with a lone pair. 3 lone pairs are there, and also a negative charge. Now what this negative charge will do, it is going to push this lone pair towards benzene. It is going to repel electron, which is something negative, towards benzene. So these 2 electrons will be readily pushed towards benzene due to resonance. The negative charge is going to push these electrons towards benzene due to resonance. So with the result, since this negative charge is going to push this lone pair of electron of the oxygen towards benzene so readily, on the benzene ring at ortho and para position, the amount of negative charge that will be developed will be very high. In the case of water as a solvent, benzene ring will be highly activated, dying to react with the bromine. Because oxygen, which has a negative charge, is going to push the electron towards benzene ring. The concentration of negative charge over here and over here will be very, very high. Because the group is pushing the electron towards the ring, so the concentration of negative charge developed at the ortho-para position is very high. So with the result, all the 3 positions simultaneously attacked by the electrophile, which in this case is Br+, and we get a tri-substitute product. So in the case of polar solvent, problem is that phenol is present as a phenoxide ion, and the phenoxide ion, the benzene ring is even more activated. The amount of negative charge present at the ortho-para position is very high, so it reacts simultaneously with Br+ at all the 3 positions simultaneously. It is highly activated. It's a highly activated ring. Now let's see what happens if you react bromines again with, phenol with bromine in the presence of a non-polar solvent. Let's say we are using carbon disulfide. It is a non-polar solvent. In that case, if you use a non-polar solvent like carbon disulfide or maybe carbon tetrachloride, you will get a mixture of ortho product and the para product. You will get the formation of 2-bromophenol and you get the formation of para-bromophenol. So in the presence of a polar solvent, we get the tri-substitute product, and in the case of, like, if you do the same reaction in the non-polar solvent, we get the mixture of ortho and para product. And just to repeat, why in the polar solvent we are getting all the 3 positions attacked by Br+ simultaneously? Because in the polar solvent, phenol is present as phenoxide ion. In phenoxide, oxygen has a negative charge. This negative charge is going to push these electrons towards benzene very readily. It is going to repel and the electrons are going towards the benzene. The amount of negative charge at ortho and para positions are going to be very high, and with the result the ring is so activated that the Br plus attacks all the three positions simultaneously and we get a tri-substituted product. So in the polar solvent we get a tri-substituted. In the non-polar solvent we get a mixture of ortho and para. So this was the first reaction called halogenation. Now we are going to discuss the next reaction called nitration. We are going to do the nitration reaction of phenol. Nitration reaction of phenol. In nitration, which groups gets attached? NO2. So let us do nitration of phenol. Let us do nitration of phenol. So if you take phenol and react it with dilute HNO3, we are going to get a mixture of ortho and the para product. We get ortho nitrophenol, which if you remember yesterday we have discussed, it is steam volatile, and we get also para nitrophenol, which is not steam volatile. Remember, this has got intramolecular hydrogen bonding and this has got intermolecular hydrogen. Intra and this is inter. Its boiling point is less, its boiling point is more. Steam volatile, it is not steam volatile. So when you get a mixture of these two products, you can subject it to steam distillation and separate out. This will go in the vapor phase along with the steam, this will stay behind. This has got higher, this has got lower boiling point. But if you take phenol and react it with nitrogen mixture, which you know is nothing but conc HNO3 and concentrated sulfuric acid, again we get a mixture of tri-substituted product we are going to get. All the ortho and para positions will be simultaneously attacked by the electrophile, because if you use a nitrogen mixture there will be so much of electrophile NO2 plus, the excess of NO2 plus is present and all the three positions are simultaneously attacked. If you remember yesterday already we have discussed, this is commonly called as picric acid, or whose IUPAC name is 2,4,6 trinitrophenol. So with our nitrogen mixture we get a picric acid, but with dilute HNO3 we get a mixture of ortho product and a para product. And how we separate ortho and para product the mixture? We can do it by simple steam distillation. This is steam volatile, this is not steam volatile, because this has low boiling point and this has got the high boiling point. So that is a reaction called nitration. Second reaction, second electrophilic substitution reaction called nitration. Now let us do the third reaction, that is called sulfonation. Again happening at ortho and para position. In sulfonation, which groups attached? It is SO3H. And who is the electrophile involved in sulfonation? It is sulfur trioxide. SO3 is an electrophile. Like in nitration, who was the electrophile? NO2 plus. In bromination, what was the electrophile? Br plus. In sulfonation, the electrophile is SO3. The group which attaches is SO3H. So we treat it with concentrated sulfuric acid. That is used for doing sulfonation. And again we'll get the mixture of ortho product and the para product. We get the mixture of ortho product and the para product. Mixture of ortho and para product is obtained. Let us give the IUPAC name of this compound. You know SO3H has a high preference over OH, so numbering will be like this. In this OH will be acting as a substituent, so it will be called as 2-hydroxy. And the rest of the compound is benzene sulfonic acid. And what will be the name of this compound? This will be called as 4-hydroxy benzene sulfonic acid. So we get the mixture of ortho and para product. Next reaction we are going to discuss is called Friedel-Crafts reaction. Friedel-Crafts reaction. Phenol 2 undergoes Friedel-Crafts reaction, but I'll just prove to you, when you subject phenol to Friedel-Crafts reaction, the yield of the reaction is going to be, or the output of the reaction is going to be very, very less. The yield of the reaction is going to be very, very less. Friedel-Crafts reaction. The yield of the reaction is very, very less. I'll tell you the interesting fact in this reaction. So if you take phenol, let's say we are doing alkylation. Let's say we use an alkyl halide, chloromethane, CH3Cl. This is the alkyl group which is going to attach on the ring. You know what is the special catalyst we use? We use a Lewis acid. anhydrous AlCl3. You know what is Lewis acid? In which central atom doesn't have an octet complete. It has got electron less than 8. So this is a catalyst. This is supposed to react, and they do react. And we get a mixture of, again, ortho product, 2-methylphenol and 4-methylphenol. 4-methylphenol. But as I told you, the yield of this reaction is going to be very, very less. Means if suppose you take 100 molecules, only let's say 4 or 5 molecules will undergo this reaction. What happens to the rest of the molecules? Let's say around 90 or so molecules. What happens to the 90% of phenol molecules? What happens is phenol is supposed to react with CH3Cl. This we are doing is Friedel-Crafts alkylation. But problem is that most of the phenol molecules, you know, in phenol OH has a lone pair of electron. Anything which has a lone pair of electron actually is a Lewis base. So phenol is a Lewis base as it has a lone pair of electron on the oxygen. So what happens is it's a very strong Lewis base. So when you mix this and this, what happens? Most of the phenol molecules, they react with catalyst, which is supposed to catalyze the reaction. But actually it utilizes phenol. It reacts with phenol because this is a Lewis acid. Aluminum octet is not complete. It is electron deficient. It just has 6 electrons around it. It's electron deficient. So when you mix this and this is supposed to react but what happens? 90% of the phenol molecule reacts with the catalyst. How? This will give its lone pair like this. It forms coordinate covalent bond. It forms a salt. So when you subject phenol to Friedel-Crafts reaction, 90% of the phenol molecules will undergo a reaction with AlCl3, which is a catalyst, and not with CH3Cl. Very few molecules will react with CH3Cl, and you will get a mixture of ortho and para product, and the yield of this reaction is going to be very, very less. So in today's class, we have discussed 4 electrophilic substitution reaction of phenol happening at ortho and para position, and happening very fast because in phenol the benzene ring is highly activated. First one we discussed was bromination, second one was nitration, the third one was sulfonation, and the fourth one was Friedel-Crafts reaction, in which you find the yield of the reaction is very, very less. We have to discuss 2 more reactions, but today we are not going to discuss those reactions. Tomorrow we are going to discuss 2 main reactions to wind up this chapter. Tomorrow we are going to discuss 2 main reactions. One we are going to discuss is Riemann-Tiemann reaction. It's called Riemann-Tiemann reaction. Again an electrophilic substitution reaction. And another name reaction we are going to discuss is called Cold-Schmidt reaction. We are going to discuss Cold-Schmidt reaction. Tomorrow we are going to also convert phenol into a very important drug called aspirin. Remember aspirin, I told you aspirin is used to relieve the pain as well as it brings down the body temperature. So this all for today's class. Please go through the video. I'll be uploading the notes also of the class, and then we'll carry on tomorrow. See you in the evening for the class on the Zoom. Okay? So take care. Have a nice day. Thank you.